Hello, welcome to this short presentation. I'm just going to begin by talking about what is PMC. And so legally, I think we have to call ourselves an academic club, just because otherwise we don't get any funding. But we're a social club. Hello. So PMC is just a social club for people who like math, and you can come and hang out with us. We run a couple different events during the term. Our specialty is Prof Talks, where we get a professor to come in and talk about some cool math that they're doing or their research, and usually it's pretty accessible to undergrad students, but none of the professors wanted to come to talk to incoming first years, so I guess you guys are stuck with me. And this talk is kind of going to be more like our short attention span math seminars, where we get like students to prepare their own talks, and then they can kind of give talks to each other. Aside from that, we also run problem of the weeks, where we publish like a problem every week, 2 weeks. And by we, I mean I don't give the other execs any credit for it. I come up with all the problems. Yeah, so the rest of the presentation is just going to be me blabbing to fill up time. Hopefully you'll find some of it cool. But if you have any questions about PMC or just in general, you can feel free to interrupt. And yeah, okay. Well, without any further ado, I just wanted to start with a problem, and I kind of like this problem. So suppose you have this bag here, this one, and it's arbitrarily large. So it can hold as many things as I want it to hold. And coincidentally, I have an infinite number of balls, as one does. And okay, here's what I'm going to do in this problem. So I'm going to start out at 11 p.m. Not in the morning. This is at midnight. So I'm going to take this ball and I'm going to put it in the bag. Just one ball. So we're going to have one ball in here. Okay. I think that's pretty good. Okay. Now 11:30, I waited a while. I have this one ball in here. So I put in one ball last time. This time I'm going to put in 2 balls. So this one's out already. I put it in. I'm going to put in this guy and this guy, next 2 balls. So got 2 and 3. And one more thing, I'm going to take out the smallest number. So 1 is going to go out there in the trash. No more 1. Okay. All right, going to wait some more time. Now it's 11:45. I've just got 2 balls in here. I put in 2 last time, so I'm going to put in 3 this time. So 4, 5, and 6. These ones are going to go in 4, 5, 6, and take out 2, because that's the smallest number. Just going to pop that. So the number of balls is getting bigger in the bag. Okay, so we got 3, 4, 5, 6. The time is now 7.5 minutes to midnight. And I'm just going to repeat this. So I had, how many balls did I put in last time? 3? Okay, so I'm going to put in 4. These guys are all somewhere else, but I'm going to take these 4 balls and then put it in. Okay. I'm going to keep doing this forever. Okay. My question is, what happens at midnight? So, if you guys want to put it in the chat, what's going to be in the bag? Is it going to be like an infinite number of balls? Is it going to be finite? And this is at midnight. Like, this isn't going to be like infinitely close to midnight, but not at midnight. Don't try to convince me that midnight doesn't exist. Okay. Universe consumed by balls, bad ending. Okay. All right. One. Oh, okay. Empty bag. Okay. And that's two different answers. I'll wait a couple more minutes. Tea bags. Very interesting. I like this problem. Checks your intuition about infinity. Give it a couple more seconds to think. All your assignments are going to be due at midnight, so midnight better exist, you know. Otherwise, you're kind of scared. Okay. All right. So this was a fun problem, and I'm going to leave it as an exercise. I'm not going to tell you the answer yet, I guess. Maybe at the end of the talk we can go back to it, but okay. All right. Let's just move on to something different. We all know that first years get math ties at the beginning of the year, where each first year gets one math tie. And MathSoc, or kind of student council, organizes this. And my question is, how does MathSoc guarantee that every first year gets their tie? You could argue that MathSoc doesn't guarantee it because MathSoc can be quite terrible at what they do, but mathematically speaking, what will they do? They count the number of first years. This was, I think, 2020. They had 2,000 students. Number of ties was 2,500. It's pretty obvious. Number of ties is more than the number of students, so there will be enough ties. Okay. But did we do extra work? See, because we didn't really need to know how many students there were, and we didn't need to know how many ties there were. So yeah, we did extra work. Okay. We didn't need to know. Okay, so how else could we have done this? Imagine if we had way more students, like a football field of students, and a football field of ties too. It's a classic example of something really, really big, is a football field amount of it. How would we know that every student has a tie? And the idea here is that we can pair up each student one tie. So we have, 3 students in the football field. And let's get a tie in here. Okay, if we've got, I'm sorry, this is going to be a terrible drawing of a tie. But we've got, say, 2 ties. This guy gets a tie, this guy gets a tie. There's 1 student left over, so, clearly there are more students than ties. On the other hand, if we had 2 more ties, some more prisms than ties at this point, but this guy will get a tie, but now we have 1 tie left over. So, that's no good. But on the other hand, we kind of want a perfect match. 3 ties, 3 students. But the advantage here is we're pairing them up, so we don't actually need to count them. So that's extra work. Kind of a neat idea. And that's the idea that you kind of learn in first year math 147. So let's kind of think of a function, and you've probably seen these in your math textbooks sometime in calculus in high school or pre-calculus. So let's imagine we have our ties, tie 1, tie 2, 3, 4, and 5, say. We pair Alex with 1, Bob with 2, Charlie with 3, and I've got some ties left over. And this is called an injective function because we can kind of intuitively see that this set of students is smaller than the set of ties. Is that okay? There. Okay. Don't see anything in the chat. So similar idea, but the opposite. We can have a surjective function. So that's when we have more students than ties. You can kind of think of this set being smaller than, oops. this set is bigger and this set is smaller, because we have 1, 2, Alice will get the first tie, Bob will get the second tie, Charlie is left over. And this is what we call a surjective function. And then just like in our previous drawing, bijective function is kind of where the Goldilocks zone. Everyone gets a tie, and everyone is happy. Yeah, 3 types of functions. Okay, all right. Now we ask the question: what would happen if instead of finitely many students and finitely many ties, where we kind of know that 4 equals 4, 4 ties, 4 students? What would it mean for one infinity to be bigger than another, or smaller than, or equal to? Okay. Intuitively, if we have 2 sets are just mathematical boxes with stuff inside, and these can be infinite sets. Okay, well, if we have, A is smaller than B, that just means that I can pair up every element in A with a unique element in B. So it's kind of like that diagram where A is smaller than B, right? This is A, and this is B. You'll have like stuff left over, okay? On the other hand, if every element in B gets paired up, that's kind of like B is smaller. So B and A. Hello. Okay. So, and then the last case is the Goldilocks zone. If both of these are true, if you've got something is less than or equal to and something is greater than or equal to, you know that it's equal to each other. And we can kind of use a formal definition of this, where if you've got an injection, a surjection, or bijection, those are exactly the terms that we defined above, but they don't really matter because they're just fancy words that you can throw around at parties and people will be impressed. Yeah, good. So yeah, what have we done here? We had no intuition about how infinite sets work. So when mathematicians kind of don't have any intuition about things, they start defining them to seem productive. And then, you go from there, because this makes sense intuitively. It makes sense for finite numbers, so maybe it'll make sense for infinite numbers, infinite sets. Okay, let's move on to different kind of thought experiment. So in the 20th century, I think a mathematician named Hilbert proposed this kind of philosophical experiment about a hotel that's infinitely long. So it's got rooms 1, 2, 3, 4, all the way to infinity. And the great thing about this hotel is that every room is full. There's a guy there, there's a guy there, and I'm not going to draw all of them, but every single room is full. So, hotel's making an infinite amount of money every night, which is pretty great for them. Here we are with our, hotel. Every room is full, but then we have the question of what happens if there's a new person who shows up. Billy here wants a room. And we can't really turn them away because we've got infinitely many rooms. But every room is full. So what can we do? Well, what if, let's see, we have kind of an idea of, okay, let's take this guy and move him to the second room. And I'm going to take the guy in the second room and move him to the third room. And then I'm going to keep doing that forever. So aside from disturbing infinitely many guests, what have we accomplished? We've got this 1 and 2 room in the beginning, and our new person can sit happily there. Okay, is that okay? Are there any questions about that? Okay. All right. So what are we thinking here? Where is this coming from? So we've got this set 1, 2, 3 of rooms, right? This is how the rooms are numbered. Now, if we numbered each person in each room as the same as their room number, 1, 2, 3, 4, 5, you know, then the new guy can be room 0, I guess, because you're kind of squeezing him in before the number 1. But we can't squeeze him in. We've got a function that maps, you know, n to n plus 1. This is the bijection between this set and this set. So a lot of people call this countable infinity because you can count it. But I like the way a mathematician named James Grimes put it, where you can list it, kind of pairing it up, then going back to the idea of pairing things up. So I've got these numbers kind of in a list right here. And can I list these numbers? Well, yeah, of course I can. I can go 0, 1, 2, 3, 4, ... And you can see this kind of defines a function where 1 goes to 0, 2 goes to 1, and so on. Or, you know, the other way, if you start from 0, go to 1, and 1 goes to 2, and so on. That also works perfectly fine. And this is the guy, James Grimes. If you watch a lot of Numberphile, you probably know who this is. It's very British. Is there any questions about that? Good with that idea, where these two infinities are kind of the same size, even though this one clearly has another element in it. Okay. Right. Okay, so this is just kind of going back to what it said, where we have a function that maps from 0, 1, 2, 3 to 1, 2, 3, defined by just adding plus 1. And this is bijection because it maps, every number can get paired up, right? And no number will be left behind. Okay, every number can be paired here, and every number has something to go to, something different. Okay. And this is, you know, pretty easy to generalize. So say you've got a bus full of, you know, 50 people, 50 new people, right? New bus. Well, you know, you could be a pain and just get, you know, do the same thing, but like 50 times in a row. I think that would be quite the pain, but you can get person in room 1 goes to the person to room 50, 51. Okay. Person in room 2 goes to room 52. And you can kind of free up the first 50 rooms for the incoming bus of 50 people. Okay. All right, so, and this is, you know, if you replace stuff with a K, it sounds fancier. Any finite K, we can just move everyone to n plus K, and then we'll free up the first K rooms. Okay, but you know, this talk is about infinity. So what happens if we have an infinite bus where there's an infinite number of seats? Okay. How will we fit them in? Well, I think the key idea here is we've got odd numbers and we have even numbers, right? We can kind of partition, because we can't split it down. We can't go like, okay, this half will be for the first infinity and then the next half, because there is no half, there's no splitting point. But if we kind of alternate, you know, what this, let's say that this person was in the hotel and we get him to move to room 2. The guy in room 2 will move to room 4. The guy in room 3 will move to room 6. So which ones will be full? I'm going to circle the ones which will be empty. We've emptied up this one, this one, this one. So all the odd numbers are going to be free. And all the even numbers are going to be taken up by hotel people, the ones who are already here. Okay. In that way, we're going to free up an infinitely many number of rooms for new people to come in. Okay. And, you know, we can generalize this to any finite number of infinite buses. So if we've got bus 1 here, and bus 2 here, and let's say bus 3, so there's 3 buses, and these guys are all infinite, right? And we want to fit them into the hotel, which is also infinite. So I'm going to draw it like this. Dot, 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 right? 1, 2, 3, 4, 5. Okay, well, what can we do? Well, back when we had only 1 bus and the hotel, we looked at divisibility by 2, right? Odd and even. Same idea here. So let's say we're going to put the people in the hotel go from n to room 4n. So a person in room 1 will go to room 4. 2 will go to 8. 3 will go to 12. Okay. All right. So every 4th room is now filled. And then we can look at the remainders. So this guy will go n to 4n plus 1. So what does that mean? So say you're in bus seat number 1, right? So we're going to go from 1 to, what's 1 times 4 plus 1? This one will go to 5. Number 2 will go to 9. Okay, it's embarrassing watching me do basic mental arithmetic, but same idea here. N will go to 4n plus 2, and n will go to 4n plus 3. And that way every person is happy, every person gets a room. And we're looking at divisibility by 4 because there's kind of 4 sets of infinity. You've got the hotel and you've got the 3 buses. Is that any questions there? Let me just check the chat. You know, 3 buses is arbitrary. If you've got k buses, then it'll still work. You can just look at every kth number. Okay. So kind of back to numbers. Can we list the integers? It's kind of simple enough. I think this is the same thing as when we had just the hotel and the first bus. Well, let's just alternate. I'll map 1 to 0, 2 to 1, 3 to -1, and 2, -2, 3, -3, 4, -4. And so we've listed all the integers just by rearranging their format, even though like if you split it down the middle, you've got 1 infinity here, 1 infinity here. So you don't really, it's hard to know how to list it. So we just needed to alternate, and that'll get us what we want. And this is just writing it out in fancy function notation. Again, we can check if n is greater than 1. So for all the positive numbers here, they'll get mapped to twice their value. So 1 goes to 2, 2 goes to 4. This is exactly like our hotel problem, where these guys are the ones already in the hotel. Okay. And then all the negatives, these are kind of like our bus people. Well, we've got the extra rooms. What do we not fill up yet? We have 1, we have 3, we'll go to 5, and so on. So using Hilbert's hotel, we can figure out that the set of integers is the same size as the set of natural numbers. You know, set of integers is integers. This is the notation for integers. This is the notation for natural numbers. Again, put them on your math assignment and people will think that you're really smart because they're fancy symbols. That's a cool idea. Okay. Any questions about that? Okay. All right. Let's go. Let's move on. Okay. All right. So we're kind of building up. We've got the natural numbers is 1, 2, 3. Then the whole numbers is a pointless distinction in terminology, but you know it's got 0, 1, 2, 3. we just looked at the integers. What about the rationals? Okay. Well, the rationals are interesting just as an aside because, you know, unlike integers, rationals, you look at a number line and I take any two rationals, let's say 1/2 rationals are just fractions, and 3/4, there's going to be a rational in between. And then between these two guys, there's going to be a rational. And between these two guys, there's going to be a rational. But between any two rationals that you can have, there's going to be a rational in between, called this density. So you'd think that they're kind of just packed closer together than integers. You know, integers, you've got 1, 2, there's no integer in between that. So can we compare it to the size of infinity of the natural numbers? Okay. All right, so this is what a rational looks like. It's a fraction. It's got 2 parts. Okay, well, maybe we can have this part be, just going back to our Hilbert's hotel kind of idea, let's have this part be bus number. And this part, this means number. Sorry, it's a hashtag. And this one be the bus seat. So what have I just said here is that I'm just gonna correspond 2/5, the rational 2/5 with bus number 2. So equal to bus number 2, seat 5. But we have an infinite number of options for the top number, the numerator, and we have an infinite number of options for the bottom number, the denominator, or as my first graders like to call it, a denominator. So, you know, what have we kind of, with our metaphor, we've got an infinite number of infinite buses. Right? So bus number is going to be our numerator. So numerators can be any number and denominator can be any number. So we have to kind of fit these into our hotel. And then 2 ideas that we can use is Euclid kind of came up with this one, that there's an infinite number of primes. And I don't know who came up with this one. It was probably also Euclid, because Euclid was smart. It was that each number has a unique prime factorization. So you can't have 2 numbers have 2 different prime factorizations, you know, up to ordering. How can we use? And if you've seen TED Ed, you probably already know this trick. So we're going to map people in the hotel are just going to go to powers of 2. So if we've got our hotel, 1, 2, 3. The person in room 1, they'll go to room 2 to the power of 1. Person in room 2 will go to room 2 to the power of 2. Room 3 will go to room 2 to the power of 3. 8. So now we've used up all the powers of 2. I'm not going to do 2 to the power of 0 because that'll make a mess out of things. But so here we are. And then the first bus, same thing, but now we're going to do powers of 3. So, you know, if you've got a bus, person 1, 2, 3, person 1 will get mapped to room 3 to the 1, person 2 will get mapped to 3 to the 2, and 3 to the 3, and so on. Just saying the same thing. And we'll just kind of keep doing this with other prime numbers. You know, bus 2 will say powers of 5, bus 3 will go to powers of 7, 11, and 13. Oh, I did not include in the slide there, but what's important here is that these rooms will never overlap. Because of that unique prime factorization, right, there's never going to be a power of a prime p to some number n and a different prime, say p star, to power m. These are never going to be equal to each other because the primes are different. every number has a unique prime factorization, so it can't have two prime factorizations. These rooms won't overlap, and we know we have an infinite number of primes, so we know that every bus will have a prime to go to. And that's kind of what we wanted. But on the other hand, as you may have seen in my slide, is that this is not a bijection because you've got rooms that are not filled. So here's our rooms. So room 1 will not get filled because we're not doing powers of 0, because every prime to the power of 0 will map to 1. So we don't want people, several people going to the same room. 2 will get mapped, 3 will get mapped, 4 will get mapped. Same with 5, but 6 won't, because 6 is equal to 2 times 3. And in our, powers of, it's not a power of 2, it's not a power of 3, it's a combination. But, and this is the interesting thing here, I think it's pretty obvious that the number of people, total people, in the hotel and the bus is going to be bigger than or equal to the number of people in the hotel, because you've already got the people in the hotel. So what we started with is already kind of bigger than or equal to the number of people in the hotel. But using this idea of mapping, that's kind of the reverse. Now we know that the number of people, we've got rooms in the hotel left over. So that means that the hotel is smaller than or equal to the total number of people. And this is a very hard thing to prove. You'll probably see in the first year. I think this is called the Cantor, Schroeder, Bernstein theorem. You might be spelling that wrong. If you're going into first year, do yourself a favor, look it up and get freaked out by it, but don't worry too much about it. It's probably just going to pop up as a bonus question. But they prove that if you've got two sets where one is less than or equal to than the other, and you know that that same set is also greater than or equal to the other, so you just kind of move that aside a little bit. So if you've got a set A is less than B, and A is greater than or equal to B, then together, this gives you that A equals B. Which is to say, if we can fit in any way, even with rooms left over, if we can fit people into this hotel, then the number of people and the number of rooms will be equal. Okay, are there any questions? It's a very complicated thing. It took 3 years to understand it. And I only learned about it last year. Okay. So another way that we can think about this is that, what do we have? We had 2/5. We're just going to associate each rational with a 2-tuple. So 2/5 is the same thing as 2,5, where the first number is going to be our numerator and the second number is going to be our denominator. Okay. And we've got infinite number of choices for this guy and infinite number of choices for this guy. So, for people who like CS, you might think of this as a 2D array where, say the first spot is going to be numerator is equal to 1, and you've got all the possible denominators, and then numerator is equal to 2, and then all the possible denominators, and so on. Or, another way to picture 2D arrays is a matrix. And this is a really great image that I found on Google. But basically, kind of going with the 2-tuple idea, this will be numerators 1, denominators 1. This one will be 1, 2, 1, 3, 1, 4. And then here it's going to be 2, 1, 2, 2, 2, 3, 2, 4, and so on. These are just different ways of representing the same thing. No one said that fractions have to be represented like that. We can represent them as pairs of coordinates. So our task now is to, list these or find a way to list them, but that's kind of complicated because, you know, how are we going to list this? Oh, I see a question in the chat. Oh, doing good, Mary. Doing really good. Heat wave in Manitoba, though. Okay. And if you've seen this before, you've probably seen it 1,000 times. You can just kind of go like this, just zigzaggy proof. You know, going along this little path. And you know, you're gonna have numbers that are repeated. You've got 2/2 and 3/3. These are the same thing as 1. You know, 4/2 is the same thing as 2/1. But basic idea is if you can somehow list them, you already know that the number of rationals is going to be bigger than or equal to the number of natural numbers, but this kind of shows that it's definitely smaller than or equal to the number of naturals. So what can we conclude? They're the same size. The number of fractions is equal to the number of numbers, like 1, 2, 3. Yeah. Okay. Is this good? Any questions? Let me get a different color out for my pen. Okay. All right. Let's take it one step further. Didn't choose very appropriate titles for my presentation, but whenever I see squares, I always think, what happens if this was a cube and not a square, right? Okay. What would that correspond with? Well, we had the set of 2 tuples before for the square. We have this be 2 tuples. So, you know, pairs of coordinates like x, y. If we want to do a cube, we need 3 dimensions. That's x, y, z. Okay. So imagine, you know, if fractions had 3 parts to them, then, you know, we could call it some other different number. And we're trying to find out if that's equal to the natural numbers in size. And here I found a really great picture of a cube online, and we can label their coordinates. You know, but if I just label the basic ones, here we are. Here's our first dimension, second dimension, third dimension, and this is going to be our origin, because the other square thing also kind of went from the top down to the right. Okay. So we're just going to look at this again, stare at it really hard to figure out, okay, well, we've got these kind of like slices, right? So this was like a 1x1 square. This was like a 2x2 square, 3x3 square, right? And they're kind of slicing them like that in order to list them. Okay, so maybe we can do something similar. Okay. Okay, I've got this really great. Didn't have time to draw the full cube, but maybe I can do this. Duplicate. One more time. Okay, we're going to draw a cube. Oops. One more time. Duplicate, and then move right here. And duplicate, and then move right here. Awesome. Okay. Oh boy. Okay, I need a different color for this. Maybe purple. So let's just kind of join all these. Oh. 1, 2, 3. Oh boy. 2. This is looking more 4-dimensional than 3-dimensional, to be honest, but that's okay. Okay. So let's start from the top kind of cube here. I'm actually going to use the diagram that we had in the previous slide because it's easier to see on this one. But well, remember how we had these kind of slices, right? So what did we do back then? Well, we took the kind of points that were 1 away from the origin, and we combined them into a slice, into one line. but in 3 dimensions, that's gonna give us a slice in 2 dimensions. So if you can see this little triangle here. Okay. Now, kind of bend your ability to see what's going on here. But okay, let's take all the points that are 2 away. 1, 2, and then in this direction 2. Should be like this. And let's connect them through lines across the diagonals. Okay, one more line, and then I think I'm missing one more line here. Yep. Okay, and now if you can see the slice, different color, this is our slice right here. Okay, we're getting triangles. Okay, you continue this, whoa, you got triangle numbers. Illuminati confirmed, but not quite. But yeah, this is the first slice, the second slice, and the third slice, fourth slice. The only thing that's kind of left is to find a zigzaggy path between them, but you can do that however you'd like. It doesn't really matter as long as you have some sort of like algorithm to do it. Let's say like that, and you'll always be able to list every single point in the 3-dimensional space using this kind of zigzaggy line. I'm taking slices. That's how we're going to enumerate the 3 tuples. Okay, but we have that whole thing with the Hilbert's hotel. And I'm wondering how we can use that metaphor again to parallel what we're doing. So with 3 tuples, we need to not just add another bus, because we already had an infinite number of buses. We need to somehow nest another level of infinity. So what if we just kind of define, okay, one city is going to equal an infinite number of infinite buses, right? And how we're going to get to that next level of infinity, let's go with an infinite number of cities. Okay, how can we fit all of those people into one hotel? Okay, is everyone good with this? No? Okay, so I had to think a bit for this one, but let's think about what we did before. Well, we took prime powers, right? So kind of going off of that, let's assign the first city will be powers of 2. Okay, so we've got 2 to the power of 1, 2 to the power of 2, 3, so on. Okay. So we've only got these rooms that we can put all of city 1, we have to put it just into these rooms. Okay. Okay. But what's in city 1? We have an infinite number of infinite buses. And we could only fit that, we could barely fit that into all of the numbers, right? To 1, 2, 3, 4, 5. And now we've got less numbers, and there's no prime powers in powers of 2. It's all powers of 2, right? But we can list these powers of 2, right? We can associate 2 to the power of 1 with like 1, 2, 3, 4. And we already know how to fit infinite number of buses into 1, 2, 3, 4, and so on. Okay, we just take prime powers again. Well, we can associate each prime power with a natural number. We just take the exponent, right? 1, 2, 3, so on. Okay. So the city 1, let's say this guy will be the first bus. Bus 1. What does that mean? So bus 1 has an infinite number of people in it. 1, 2, 3, 4. This guy will go 2 to the power of 2 to the power of 1. This guy will go to 2 to the power of 2 to the power of 2. Oops. This guy will go to 2 to the power of 2 to the power of 3, and so on. And this is just for the bus 1. For bus 2, switch colors. This is going to be bus 2. Bus 2 is going to get all the powers of 2 that are powers of 3, you know, where the exponent is powers of 3. So if this was bus 2, then this will be 2 to the power of 3 to the 1, 3 to the 2, 3 to the 3. And using the same logic as before, none of these rooms will overlap, right? Because none of the exponents will overlap. And then same idea. For city 2, we're going to take a different base. And this will be the first bus, bus 1 of city 2. This will be the second bus. And this will be the third bus. Okay, all right. Okay, and then, you know, moving on with the same kind of idea where city 3 will get the third prime. Okay. Can we generalize this even further? Because right now we just listed the set of 3 tuples, right? We showed that we can enumerate the 3 tuples in 2 different ways. We had the cube kind of diagram, which paralleled how we enumerated the rationals, and then we had the prime kind of proof. But 3 is kind of an arbitrary number, right? There's nothing stopping us at 3 dimensions. So what if we went to n dimensions? We can just kind of extend that idea. So, you know, if you, instead of cities, after cities, you can say like, okay, an infinite number of cities is 1 country. Okay, let's go. 1 country is equal to infinite number of cities. 1 city is equal to an infinite number of buses. And 1 bus has an infinite number of people. Okay. Can we fit, we can fit 1 country, right? Because what we did was we had 1, you know, infinite number of cities, infinite number of buses, and infinite number of people. We can fit 1 country into our Hilbert hotel. Can we fit an infinite number of countries into our Hilbert hotel? Well, we can't, using that same idea. We just keep doing prime powers. You know, 2 to the power of 2 to the power of n, 2 to the power of 2 to the power of 3, and 2 to the power of 3. Oh, oops, 5, and this will be for the first city, and no, for the first country. This will be our first country, country 1. Oh, I see something in the chat. I think this is a great idea. You know, you could just stack primes. There's just so much space in this 1 hotel. You've got 1 hotel, and you can, and you know, there's nothing stopping us at 1 country or at infinite number of countries, because those are just 4 tuples. We can keep nesting infinities for, you know, as many times as we want, and we just take bigger and bigger towers of primes. Okay. Yes, Catherine. Okay. Can we take this further? Okay. We have fit a lot of infinities into one hotel. Catherine, I would like to remind you that this meeting is recorded and it is a part of MASOC, you know, official event.
I'm perfectly okay with that. I said what I said.
Okay. Okay, so we had any number of tuples we can put into our hotel, right? Our country, just for reference. Infinite number of countries would just be 4 tuples, and I need another. Let's go with alpha. Okay, so those are 4 tuples. We can fit those in. Okay. What if we had an infinite number of nests of infinity? So in other words, infinite dimensions. Back then we were working with like a 3-dimensional cube. We could do 4-dimensional in theory, 5-dimensional. What if we had infinite dimensions? Or same idea, infinite tuples. So could we have, you know, I'd need an infinite number of letters here, but A, B, C, D, so on and on. Can we fit all of these tuples into our hotel? Okay, Catherine, you're waving your head. Okay. Oh, yeah, we got the right idea. So this is one infinite tuple is just one real number, and between 0 and 1. Okay, because you can express any real number as 0.x1, x2, x3, and so forth. Can we map all the real numbers to our hotel? No, and this is due to this guy right here. Very great guy, Cantor, who had this great proof, diagonal proof. And if you've seen it before, not Vladimir Lenin. He does not come into set theory at any point, but he had a Cantor, on the other hand, had a great proof of why the real numbers can't be listed. Right? That was kind of another characterization we had of fitting numbers into a hotel, is being able to list them into the hotel rooms. Okay, so let's kind of assume that we could. Let's say that there's some possible ordering of all the real numbers as a list. So we can have other numbers here: 0.98765 and maybe just a bunch of ones, right? Let's say there's an arbitrary listing. Okay, all right, this is getting compared to the bourgeoisie now. I am scared to check the chat now. Okay. So what did Cantor do? Well, this is not a big surprise, again, if you watch any sort of number file or TED Ed, or you've done like first or second year math, but okay, he looked at the first digit of the first number, whatever it is, and you can change it. Let's make a new number that's not on the list. The first digit here is a 1, so I'm going to put a 2, and whatever number I'm creating here, definitely not the first number, definitely not equal to the first number, because it differs in this first digit. Then he looked at the second digit of the second number. Okay, it's a 2 here, so I'm going to put a 3. Okay, so this number, whatever number I'm constructing here, definitely not equal to the second number. Let's go to the next one. Let's go look at the third place value of the third number, and it's a 4, so I'll put a 5. Okay, definitely not equal to the third number, because the third place value doesn't match, right? And you can see why this is called a diagonal proof. They line up quite nicely. So every time I look at the place value and that corresponds to the number on the list, and I choose a digit that's different. And then I know that this number, whatever it is that I've constructed here, it will definitely not equal any of these numbers. So it is not on the list, but we wanted in the beginning that this list contains every real number. So we have a contradiction. Yay, they're different sizes of infinity. Even though we could fit so many infinities, just the real numbers break everything. Okay. All right. So I think we are out of time. I'm not going to go through this proof. It's a very great proof about how the power set, which is the set of all the subsets of a set, how the power set is bigger. So it's not equal to, strictly bigger than any set. If you take any set, you take a set of all of its subsets, that set is going to be bigger. It's not going to be equal to. And that kind of proves, beyond just that we have the real numbers are greater than the natural numbers, strictly bigger. It gives us a whole host of sizes of infinities, because you can just keep taking power sets. I'm not going to go through that proof because it's complicated, and I am not going to cover it in 1 minute. And then just for reference, this might come up on a bonus question on your exams in first year, is that what is the continuum hypothesis? It's just a theorem or a hypothesis that there's no infinity between the infinity of the natural numbers and the infinity of the reals. These were different sizes, but we don't know if there's a size in between. And the cool thing about it is it doesn't matter. You can assume that there is or there isn't, and it won't break math either way, as far as we know. So that is definitely a good spot for further reading, as they say in my lecture notes. Okay. All right, that is it for the talk and me blabbing. If there are any questions about the talk, about math, or about the Pure Math Club in general, you can feel free to ask. You can join the club. We are very active right now. If an exec could post the link to the Discord in the chat, that would be great. Oh, yeah, Catherine?
How'd you get so cool?
Me? I joined
Yeah.
PMC.
Okay.
Obviously.
Is there a membership fee right now?
There's no membership fee. It is absolutely free. You can join. Anyone is free to join except for engineers. Apologies to any engineers in the crowd right now. But thank you, Evan, for posting the link. You can come. You can join. We discuss math. Yeah, there's no pressure. Okay. I think the VPI is going to kick me out if I don't end the call. But thank you, everyone, for coming to listen. Yeah, I hope to see you in the Discord. Okay. Bye. Crap, how do I end the call? Okay. There we go. Okay. Bye. Thank you.